applied mathematics, pure
Um,
mathematics?
I did both, so I have some elements of applied mathematics and also pure mathematics, and a little bit of statistics.
Okay. And now, what is your plan after AIMS?
The plan after AIMS is to continue this field of analysis of partial differential equations.
Oh, interesting. Good. Good. I think now is 4:30 and Timukai also has joined us. Barry also has joined us. So on the call we have Barry, we have Timukai, and we have Prof. Jordan. So you can start when you are ready. Are you ready?
Of course, I'm ready.
Okay, you can start.
Thank you very much for joining this talk. I'll be talking about Lie group analysis of a nonlinear coupled system of KdV equations. A brief outline of this talk, so I'll give a small introduction. Then after, I'll briefly talk about Lie group analysis, including by Lie group analysis. Then I'll talk about KdV equation. So under KdV equation, I'll touch on symmetries. I'll also talk about solutions. And then I'll also talk about conservation laws for KdV equation. Then I'm going to couple KdV equations. I'll repeat the same. I'll talk about symmetries, solutions, conservation laws. Then I'll conclude by some implications of this work. Now, nonlinear partial differential equations are used in the formulation of fundamental natural laws and even technological problems. So after formulating these problems, for us to understand the systems they represent better, we must be able to find a way of finding solutions so that we describe the systems, the state of the system at the present time, the past, or in the future. One of the methods that have been developed by researchers to find solutions for nonlinear partial differential equations is Lie group analysis. Lie group analysis was started by Sophus Lie in the year 1890, introduced the notion of Lie groups, and this method uses the invariant properties of the partial differential equation to give solutions. It's a very powerful method which is highly algorithmic. I'll give an analogy of a microscope which you use in biology to see very tiny objects. Lie group analysis provides a framework for seeing the symmetries of a partial differential equation, which is otherwise not easy to see. But with these algorithms, we're able to find symmetries of nonlinear PDEs and use them to find solutions. A symmetry is simply a transformation which maps an object, which leaves an object unchanged, or an action that leaves something unchanged. In the sense of partial differential equations, a symmetry maps solutions of the PD onto other solutions. Now, some solutions get mapped to themselves. So, for example, if I talk of a symmetry of a circle, if you fix the center and rotate the circle through a small angle, 360 degrees, all the points will map to themselves, invariants. So we also have some solutions being mapped themselves. Now that gives us two ways of finding solutions using symmetries. We either transform solutions which we know, or we find group invariant solutions. We can also use symmetries to find conservation laws. Now to show how we use symmetries to find solutions for PDEs, I choose KdV equation, which is ut plus 16x plus 2xx 0. I'll refer to it as delta. This is a third order equation. There's a nonlinear quadratic term, and it has a linear dispersive term. There's also an evolution term. This equation was derived in the year 1895 by Gustav de Vries and Korteweg to describe the propagation of shallow water waves. So this means the waves have long wavelengths and they have small amplitudes. So we shall see more the role of the nonlinear and the linear terms as we look for solutions. But first, let us find solutions of this equation before we use before you the symmetries to find solutions. I'll start with a group of transformations of the variables. So u is a dependent variable. It depends on the time variable t and the space variable x. So I'll start with the transformation. Let's say the variable t is mapped on some function of the space variable, the time variable, and depending also on some group parameter. Same for the space variable x, also depending on some function of the time variable, space variable, and the group parameter. Same to u. Then so far solution that we can always take the first order Taylor series approximation. So that means we approximate a transformation of t with the value of f on 0 plus the first partial derivative. We evaluate this on 0, where e is the group parameter. We do the same for g and u, and we get what we call infinitesimal transformations. So if I call this some tau, then I will have some taking all the other terms have been ignored. So the variable t will be mapped to t plus some function tau times the group parameter. The variable x will be mapped x plus some function, and also u will be mapped to u plus some function. So this t, psi, and eta are called infinitesimals, and they are functions of the space variable, time variable, and the dependent variable. Now, this gives me infinitesimal transformations, and to this infinitesimal transformation, we can associate a vector field of the form t del over del t plus psi del over del x plus theta del over del u. This is a vector field of infinitesimals, and we shall call this a symmetry of the equation if its third prolongation annihilates the KdV equation on all its solutions. I'm taking third prolongation so that I know how the derivatives transform. So third, because KdV is third order. And when you solve these are called determining equations, you'll find that KdV equation has 4 symmetries. So there is time translation symmetry, there is space translation, there is what we call the layer boost, and lastly there is a scaling symmetry, which simply transforms the variables by scaling them, multiplying them by constants. The time translation only transforms the time variable, all the other variables are constant. Same for the space translation, it only transforms the space variable, u and t, and constant. Now that we have these solutions, how do we use them? Now that we have this symmetry, how do we use them to find solutions? But first note that these symmetries form what we call a Lie algebra. And some of the properties of a Lie algebra are effectively shown on table 3.1 of the document, which you can refer to. So as I mentioned earlier, there are 2 ways of using symmetries to find solutions. The first method, the first approach, we use symmetries to transform a known solution to another solution, because we know symmetries map solutions of the DD into other solutions. So if I take, for example, the space variable, the space translation symmetry, then I solve Lie equations. So I have partial t, the TdE is 0, because this only acts on the x variable. So the x e is 1, and du e 0, where t bar, x bar, and u bar are the transformed variables. Solving this, so you get that t bar is some constant, x bar is the group parameter, which is the variable here, plus some constant C2, and u bar is some constant C3. Then when you apply the initial condition, so the initial condition that, for example, t bar evaluated on E is t, and x bar evaluated on E is 0, is x, and u bar evaluated on E0 is u, we get the group t bar is mapped to t, x bar is mapped to x plus e, u bar is mapped to u. Now with this transformation, if we have an arbitrary solution of the equation, if you have an arbitrary solution, let's say ut of x, if this solution satisfies, if this function ut of x satisfies the KdV equation, then by Lie invariance criterion, we can show that a function of the transform variable x, which is x plus t, and the transform variable t, which is just t, will also be a solution. This is by Lie invariance criterion. We can also use find solutions. We can also find invariant solutions. Sorry. So, for example, if I use the space variable x, the same space variable, then I solve characteristic equations. So dt on 0 is dx on 1 is du on 0. These are called characteristic equations, and it simply shows you that the variable t is not changing, the rate of change is 0, the variable u is also not changing, so they are actually invariants. Or you can separate this and take two at a time and solve. So you'll find two constants, j1 is t, and some j2 is u. You know u is a function of t from the equation, so u is a function of t, will be a solution of this. When you substitute this in the equation, you find that u bar, because there is no x, so all the x derivatives are 0. So you only have phi prime of t, 0, which tells you that u is a constant solution. So by using characteristic functions from the space translation symmetry, we find a constant solution using this symmetry. There's also a very interesting kind of solution we get specifically from the KdV equation. If I take a linear combination of the space translation and the time translation, I get this symmetry. And when I take characteristic equations of this, so I have dx on c is dt on 1 is du on 0. Only u is an invariant, x and t are both varying. So the first invariant is u. And when I solve these two, I'll get the second invariant as x minus ct. Then I'll get some u is a function of x minus ct, which if I substitute in the KdV equation will give me the so-called traveling wave solution. So now u is some function of x minus ct. So u is c over 2 sec hyperbolic squared with c over t with x minus ct, where this c is the velocity of the wave. Now these are called soliton solutions or traveling wave solutions. And you can see from the equation, they come as a result of a cancellation effect of the nonlinear term, the quadratic nonlinear term, and the linear term. The nonlinear term, what it does is it localizes the wave. It makes it as narrow as possible in the base and as tall as possible. And the linear term is also called the dispersive term. It makes the wave spread. So as a result of that cancellation of this, the dispersive term and the dissipative term, we get traveling waves of soliton solutions. We also use symmetries to find conservation laws. A conservation law is simply a mathematical expression that describes invariant properties of a system that's evolving. In the year 1918, Owino found a connection between symmetries of a PD and the conservation laws. But the theorem that Owino gave has some weaknesses. So, for example, it cannot be used for all other equations. And KdV equation is a perfect example of an equation where Noether's theorem cannot be applied in finding conservation laws. So many researchers have worked on this to try to generalize Noether's theorem for all equations, evolution equations, and even all other equations. In the year 1993, Peter J. Olver, in his book Applications of Lie Groups in Differential Equations, collected works of several authors and researchers and came up with a method called a method of multipliers. So a multiplier is just a function of, in the case of KdV, a function of this time variable, space variable, and the dependent variable. This is if it is zero order. It only depends on the dependent and independent variables of the equation. So this is simply a function which multiplies the equation and converts it to a conservation law. So I expect that if I multiply the KdV equation delta by this function, I will get some divergence expression dt over dt plus dx or dx, where dt is called conserved density and tx is spatial flux. So this will give me a conservation law. We only require that the variational derivative of the product of the multiplier and the equation vanishes. This is the only requirement. So this is the determining equations for the multipliers. And for the KdV equation, we have three multipliers: 1, u, and tu minus x of 6. This will give me three conservation laws, which have been physically interpreted as conservation of mass, conservation of momentum, and conservation of energy. And this is why in the evolution of the solitons or solitary waves, after interacting, the waves re-emerge as separate entities. Even if a wave has higher speed, it overtakes another one, they don't match. They re-emerge as separate entities. On to the coupled KdV equation. We obtained a coupled system by starting with a complex valued KdV, complex KdV defined in a complex plane, and then we separate in real and imaginary parts to get a system. Delta 1 is u2 plus alpha ux minus alpha v dx plus beta ux 0. Delta 2 is vt plus alpha uv x plus beta vx 0. This is a coupled system. Why is it coupled? Because you have the same dependent variable in both equations. So, for example, I have u in the first and u in the second. So it's coupled. That means you cannot solve the first equation without the second one. You have to solve the two of them at the same time, or simultaneously. Now, symmetries of this system is found in the same way. So you will find third prolongation, or you first start the transformation of the variables, then you find the first order Taylor series approximation to give you infinitesimal transformations, and then after that you'll find the third prolongation because you have third derivatives. And this also gives four symmetries. So we have space, time, space, we have Galilean boost, alpha dx plus du, and we also have a scaling, 3t dt plus x minus 2u du minus 2v dv, scaling symmetry. These four also form a Lie algebra, and some of their properties are shown in table 4.1. Some of the properties of a Lie algebra are shown in table 4.1. We can also use the same way we did for the single KdV equation. We can also use these symmetries to find exact solutions. So this is very important because with these symmetries, for example, if I pick the time translation symmetry, then I will get a Lie group. I'll solve the same Lie equations and I get its unity that is transformed. U, V, and X are not transformed. So in the same way, if I have some arbitrary solutions U and V, then the functions U of t plus E, X, and V of t plus E, X will also be solutions. We can also use, I want to explain, in the process, you have what we call symmetry reductions. So this is where instead of solving the original PD, you now solve a simpler problem. So for example, if I start with the space translation variable, then I have characteristic equations. Dt on 1 is dx on 0, is du on 0, is dv on 0. And effectively, this gives you three invariants, u, t, and x. So if you take u is some function f of x, and v is some function g of x, Then you substitute in the system. So there is no time variable, so this evolution terms collapse, and I will have a new system alpha f fx minus alpha g gx plus beta fxx is 0, and alpha fg x plus beta gxx 0. This is now a reduced system. So we've reduced coupled system of PDEs to a coupled system of ODEs. Now ODEs are comparatively easier to solve. We are not saying it's easy to solve ODEs, but comparatively easier in the sense that you now have only one degree of freedom or one independent variable, as opposed to PDEs which have more than one independent variables. We can also do the same, use symmetries here to find conservation laws for the coupled system. So just as I have mentioned, there have been several attempts to generalize Noether's theorem, and we also used the multiplier approach to find conservation laws for this system. And for the coupled system, the multipliers of second order were used. So the functions depend on up to the second space derivatives of the dependent variable. And for this case, we got 8 pairs of multipliers. They exist in pairs because we have 2 equations. And this effectively gave us 8 conservation laws. 3 of them, just as for the single one, represent conservation of mass, momentum, and energy. Not all conservation laws will have physical interpretation, as we are about to see. So after 1993, the work of trying to generalize Noether's theorem continued. And in the year 2006, an ancient mathematician by the name Ibrahimov made a step towards this generalization. He defined what we call adjoint equations. So for this nonlinear system, you define a nonlinear adjoint system. For this, you can look at equation 4.326 and equation 4.327. The adjoint system for this delta 1 and delta 2. And in the same year, he was also able to prove that these adjoint equations inherit the symmetries of the original system. So this is so nice because I don't have to find again the symmetries of the adjoint system. We just use the symmetries of the original system because they inherit those symmetries. So it means the same symmetries that the original system has are the symmetries that the adjoint system will have. Then with this now, he was able to define a Lagrangian for any arbitrary nonlinear PDE, where the number of dependent variables is the same as the number of equations. And we are so lucky in this case, we have 2 equations in the system with 2 dependent variables u and v. So we can apply Ibrahimov's theorem to find conservation laws. And to apply Ibrahimov's theorem for this case, we define Lie characteristic functions. So if I take, for example, the space translation, then the Lie characteristic functions, the first one, because I have 2 variables, so we'll have 2 Lie characteristic functions. So the first one is minus partial derivative of u with respect to x, and the second one is minus partial derivative of v with respect to x. Then he gave a framework of finding conservation laws using these Lie characteristic functions. So there is a formula where we just insert the characteristic functions and find conservation laws. Now, we find that for the KdV equation, for the coupled system of KdV equation that we have here, we will have for each of the 4 symmetries. So Ibrahimov's theorem says that for every local symmetry, there exists a local conservation law. So that means if we have 4 symmetries, we will get 4 conservation laws. Now, for the coupled KdV equation, the functions f and g, arbitrary functions, which are just solutions of the adjoint system. They are also form part of the conservation laws. That means these conservation laws are infinitely many. So this is a phenomenon which was first discovered by Robert Miura in the late 1960s when he was working on KdV equation. After finding the 10th conserved vector of the 10th conservation law, he showed that there exist infinitely many conservation laws for KdV equation. And the fact that the arbitrary functions f and g appear in our conservation laws show that KdV equation actually has infinitely many conservation laws. As I had mentioned earlier, not all conservation laws have physical interpretation, but that does not mean they are useless. In literature, conservation laws have been used to find exact solutions of PDEs, which will be future work for this because we have found conservation laws. So we now want to investigate how we can use these conservation laws to find solutions. Conservation laws have also been used to reduce PDEs. So you have a system of PDEs and then you reduce it to a simpler problem, which is easier to solve. Conservation laws have also been used to design numerical solvers of PDEs. They have also been used to describe qualitative properties of solutions. So this means qualitative analysis. So it means without getting the solutions, we are able to describe the behavior of the solutions. Conservation laws have also been used in numerical analysis. So they help us find numerical approximations to solutions. The exact solutions for the KdV equation are called them special exact solutions. Finding general expression for solutions of nonlinear PDEs is still a problem. So even with the Lie group analysis, we are only able to find special exact solutions. And these special exact solutions help us in very many ways. So one of the very many uses of these special exact solutions is, for example, to describe the dynamics of the system being represented. For example, let's say you're describing flow of fluid, let's say in the Navier-Stokes equation. Then the special exact solutions give you special instances. Thank you. Give you special instances. So, special exact solutions. You are able to describe special cases, for example, of fluid flow. The special exact solutions also help us to design numerical solvers. So if I know a solution, an analytic solution of a problem, then I can use that to test a numerical tool, which I can now apply in a problem solution I do not know. But I first start with what I know. And of course, with this, we can describe the system and understand the dynamics better. Thank you.
Thank you very much, Joseph. Very good presentation. Thank you very much. And now maybe we'll go to questions. So we'll start by the examiner. Prof. Jordan, do you have any question for Joseph?
Hello, Joseph.
Hello.
I'll wait for you just to finish cleaning. Yeah, but okay, you're fine.
Yes.
So well done. First of all, I really enjoyed your report. It was very well written.
Oh, thank you.
And you also gave a very good presentation.
Thank you.
In your report, I only really picked up issues in the references, and I did upload. So it's your whole report. I actually negligible errors. There was nothing really that I picked up, but in the references there were. So this is just something to pay attention to in the future, that you don't neglect the references, that you make sure that you have the title spelled correctly, the authors correctly, etc. It's just a small detail that's important to watch out for. But all in all, very, very good, very careful work. So in the introduction to section 3 and in your talk also, you gave a nice interpretation of the physical meaning. It's okay, you don't have to page there. I'll tell you now where you can go.
Oh, okay.
You gave a nice physical meaning of the KdV equation. So you were explaining the role of the nonlinear term and the third order derivative term, and what that means in terms of stretching the wave, etc. So I just would like to know, for the solitary wave solution, the soliton solution, or the traveling wave solution, that's your equation 3.2.63. Can you give an interpretation of that solution? I'll just wait for you to get there.
3.2.63.
Yes. Can you give an interpretation of that solution in terms of the speed and the amplitude of the wave and what the solution actually means about how the wave travels?
An interpretation of the solution. Okay, so we have the solution is U is C on 2 second squared of C on 2 X CT. So in this solution, C is the velocity.
Yeah.
C is the velocity of the wave.
That's right.
Velocity of the wave. And from this, I can also say that the velocity of the wave depends on its amplitude. So the taller the wave, the faster it travels.
It's exactly.
And the shorter the wave, the slower it travels.
Yes. Yeah. Because they're proportional, the amplitude and the speed or the velocity are proportional to each other.
Yes.
Right. Thank you very much. Then I'd just like to go back to the coupled KdV. So that's equations 4.1.3 and 4.1.4. Thank you for explaining very clearly what you mean by coupled. And what I'd like to know, is it possible to write this the coupled equations as one higher order equation?
Writing the coupled equation as one higher order equation. That's a very good question. I said that we cannot use Noether's theorem to find conservation laws for odd order equations. And KdV is an example of an odd order equation. So one of the attempts we can make is to increase the order of this KdV equation to fourth order, so that now we have an even order equation, and see if we can apply Noether's theorem. So for this coupled system, if I make the substitution, let's say U is some let's say U is some F(x), for example, for the first system, better one. Then where I have UT, no, it's the other way around. No, let me think. Give me some 30 seconds.
Joseph?
Yes.
I don't really expect you to do the detail right now. I think you've answered my question in terms of what I want to.
Yeah. So for example, this one ut will become fxt. So the first term, evolution term is going to fxt, and the higher order term uxx from this one will get fxx. And now you can also do the same for the second one and get now fourth order equation.
Right. Thank you very much. Okay, my last question is the work in section 4. Has it been published before?
Section 4.
Yes.
You mean chapter 4?
Yes,
Then having a couple of KdV equation.
Yes.
I do not know. I'm not aware if it's been published before, but this is what I did. This ones I did myself. I've not
Okay.
used any.
All right. But chapter 3, obviously, you took from textbooks. It's classical work, right?
Chapter 3.
Yes.
Chapter 3, the only bit that I took, which I've referenced, is when I was looking for stationary solutions.
Mm-hmm.
And I referenced where I get the Weierstrass elliptic function.
Mm-hmm.
That is the only bit which I referenced, but the rest I did myself.
Okay. All right. Thank you.
Thank you.
Okay, thank you very much, Prof. Jordan, and thank you, Joseph, also for your question. Now I will read maybe your supervisor questions, but I will share my screen. You will tell me if you see. Okay, do you see the question?
I only see, I am seeing you. Just written presentation wrong.
Okay, but I can just read you the question, even if you don't see for now. He said, describe briefly what you understand by Lie group analysis.
What I understand by this group analysis.
Yes, briefly.
Give me some seconds to collect. Okay, Lie group analysis, my understanding, is simply a method which uses invariant properties of the PD or of the OD to find solutions. So it involves finding symmetries and then using the symmetries of the given equation to find group invariant solutions. And if you have solutions which you know, for example, the constant solution, you can transform the solution, so transforming known solutions, and the symmetries can also be used to find conservation loss.
Okay, thank you very much.
That's what I
Second question. Okay, second question. How would you define a Lie point symmetry of a differential equation?
Lie point symmetry of a differential equation. That's a very good question. So all the symmetries, first of all, let me start by saying that all the symmetries that I found in this project are Lie point symmetries. When I was describing the transformations, I'm sorry I have them, but I had, for example, T is mapped to some T to some tau epsilon. I stated categorically that these infinitesimals are functions of the variable. So the dependent variable U, the independent variable T, and the independent variable X. When you have your infinitesimals being functions of only the independent and dependent variable, you get what we call a Lie point symmetry. So there are other symmetries which do not necessarily depend on just the dependent variables. If they depend on the first derivatives, then you get what we call contact symmetries for the equation. If it depends, this is if the infinitesimals depend on first derivatives, you get contact symmetries. But if they depend on higher order derivatives, then you get what we call generalized symmetries, or some people call them Lie-Backlund symmetries. But for the Lie point symmetries, the infinitesimals are strictly functions of the dependent and the independent variables. But there are other types of symmetries. So I'll give you two examples: contact symmetries and generalized symmetries. There are other examples of symmetries.
Okay, thank you, Joseph. There is a third question. What is the use of calculating a leap point symmetry of a differential equation?
What is the use of calculating a leap point symmetry?
Of
I
a
think I
differential
answered that
equation.
question before, so let me just repeat. We use symmetries, number one, to find invariant solutions. And we also use symmetries to find, to transform known solutions. So I started by saying a symmetry simply transform a solution to another solution of the PD or the ODE. It turns out that some solutions, when you transform them, you still get the same solution, the invariant solution. So that is the idea we use to find invariant solutions. And then transforming known solutions, if I already know a solution, I can transform it to and get another solution. We can also use symmetries to find conservation laws, as I have shown using Ibrahimov's theorem, and even Noether's theorem, in case the problem is a variation of problem, if it admits a Lagrangian.
Okay, so it's the same as calculating leap point symmetry, the answer that you just gave.
Calculating. You asked me what is the use of calculating a leap point symmetry.
A leap point symmetry. Okay,
After
yeah.
I've gotten a leap point symmetry, what do I use it for? And I've said,
Okay.
I use it to transform a solution that I know to another solution, or I use it to construct group invariant solutions. I can also use it to find conservation laws.
Conservation law. Okay, exactly. Thank you. There is a fourth question. What is the difference between a solution and a group invariant solution of a differential equation?
Difference between a solution and a group invariant solution.
Yeah.
Give me some few seconds to think. Okay, let me put it this way. So we are saying that symmetries transform solutions to other solutions of the PDE. So for example, for the KdV equation, if I have a function utx, if this function admits the KdV equation, then I call it a solution of the equation. That's the basic definition of a solution of an equation. So if you have a function which admits this solution, then admits this equation, then it's a solution of the equation. Now, transforming these solutions to other solutions, it may happen that when you transform the solution, you still get the same solution. So for example, let me give an example. If I have a solution, let's say the constant solution, and let's say I'm on the space translation invariant solution, where I'm using the space translation symmetry, sorry, where t is mapped to t, and x is mapped to x plus e, u is mapped to u. Then, when I transform this solution, I will still get u of t plus, t, and then x plus e, which is still a constant solution. So I still get the same solution by transforming it. This is what we call a group invariant solution. So the difference between a solution and a group invariant solution is that a group invariant solution is transformed into itself by the Lie group. So a group invariant solution is simply a solution which is transformed into itself by the Lie group. While a solution is any function which admits the equation.
Okay, thank you very much. There's a last question from your supervisor. What is a conservation law and describe method for finding conservation laws of a differential equation that you know?
So
what is a conservation law first? And after, describe method for finding conservation law of a differential equation that you know.
So in the second part, you are saying I use another differential equation that I know, or generally methods for finding conservation laws.
So first of all, what is a conservation law?
Good. A conservation law is simply a divergence expression which vanishes with the solutions of the ODE or PDE and describes invariant properties of the system that it describes. So, for example, conservation of mass. If you're describing, let's say, flow of fluid using Navier-Stokes equations, we know that mass is one of the physical properties which is conserved. So you can have a conservation law which tells you that mass is conserved. So, for example, for the KdV equation, we have using the multipliers, you get the conserved density U using the multiplier 1. And
okay, Joseph, 1 minute. The second part of the question is describe method for finding conservation law. So you are answering to this question.
I'm still on the first one. What's a conservation law?
Okay.
I'll go to that shortly. Then the spatial flask with 3u squared plus u x. Then this expression, so if I apply dt on u plus 3x on 3u squared plus u xx, it can be shown that if you take, assuming t, the density and the flux are integrable, then the integral from minus infinity to infinity of u to x is constant. And this integral represents the mass of the system. So this shows you that in the evolution of the solitary waves, or the traveling waves, the KdV equation, mass is conserved. Now, what are the methods for finding conservation laws? So for any differential equation, I've used two methods in this one. The first is the method of multipliers. I should start by Newton's theorem. Multipliers, and then Newton's theorem. Newton's theorem. So Newton was the first to find a connection between symmetries and conservation laws. And our theorem says that for every local symmetry, there is a conservation law or a conserved vector. And Newton's theorem can only be used for systems which admit a Lagrangian. And these systems should not be of odd order, so the system has to be of even order. And it was leave the variational integral invariant. Only then can you apply Newton's theorem. Now, as a result of this inefficiency of Newton's theorem, because it does not apply the general case, there has been work to try to generalize, to find a method which can find conservation laws for any PDE or ODE. One of them is multipliers, which is just a function that converts the equation to a conservation law. And we've shown in this work how to use multipliers to find conservation laws. So you can choose to use either zero-order multiplier, where the multiplier is just a function of the dependent and independent variables, or you can increase the order to get more conservation laws. So you can have first order, second order, just as I used second order for the coupled system. Then Ibrahimov's theorem is now for all PDEs where you have the same number of equations as the number of dependent variables. So for coupled KdV, you have two equations and two dependent variables. So you can apply Ibrahimov's theorem, and here you need to define adjoint equation, and then with the adjoint equation, you can find a Lagrangian, any PDE, and then find a conservation law. There are other methods. There's a method called partial Lagrangian. This one I was reading when I was still learning this field. I read this method. It was discovered in around 1999. I'm not sure of the year, but it's a very recent method, and it was also trying to generalize Newton's theorem. And the people who discovered this, Kara and Mahomet. Kara was a PhD student of Mahomet. I think they were at the University of Wits in South Africa. These are the only methods I know, but I'm sure there exist others. So the other one I can guess is using, there are softwares for finding conservation laws. For example, Mathematica and Mappon. They have libraries which can help you find conservation laws at just the click of a button to find conservation laws. So Luther's theorem, multipliers, interactive partial regression, and then softwares. These are the ones that I know. Maybe there could be others.
Okay, thank you very much, Joseph. That was all from your supervisor. So maybe Barry, do you have any question for Joseph?
Thank you, Joseph. I enjoyed your talk very much. So most of my questions you've answered because in the general discussion, but you spent a lot of time talking about the importance and the value of the conservation laws. And then at one point you mentioned that for the Korteweg-de Vries equation, there are infinitely many conservation laws, that was proven. Is there, what does that really mean? Does that, you told us the uses, like to find exact solutions to reduce PDEs and find numerical methods and so on. What is the the fact that there are infinitely many conservation laws? Is that something special?
Oh, nice question. And I didn't mention this. Thank you for this question. The fact that KdV equation has infinitely many conservation laws means that the system is completely integrable. So completely solvable. So you can find, for example, for KdV equation, you can find solutions by integrating it on prescribed initial conditions. It means the equation is completely integrable. But having an equation not having infinitely many conservation laws does not preclude complete integrability. So you might have some equations which do not have infinitely many conservation laws, but which are still completely integrable.
Okay, so it's sufficient, but maybe not necessary. Thank you.
Welcome.
Thank you very much.
Okay, thank you, Barry. And now, Simukai, do you have any question for Joseph?
Joseph, thank you for your presentation. I enjoyed it very much. And I liked how you also talked about the history of the methods that you were applying. So just one general question, actually. What did you find most challenging about doing this work?
What did I find most challenging in this work? Good question. One of the challenging things in this work was learning, I guess it's just learning the material. Because I didn't have a background in symmetry analysis before, but I've done differential equations. And in my undergrad, mostly we used concepts of functional analysis to find solutions of PDEs and Ds. So we prove properties like existence and uniqueness, regularity, before you find solutions. But symmetry analysis is based on local finding solutions defined locally in a point. So you find solutions which are continuously defined in the neighborhood, a small neighborhood of a point. This was a completely new idea for me, and it was not easy to learn. And the other challenge was finding the symmetries. Because for this work, I did not use any software, Marple and Mathematica. I only came to learn of them at the end after finishing that, oh, you can use these softwares to find symmetries. So if you look at this document, you'll find that the equations for solving symmetries, they are very long. Very, very long symmetries. A lot of work. That's the only challenge I had for this one. Everything was fine. just the very long calculations.
Thank you, Joseph.
Welcome.
Okay, thank you, Simukai. Prof. Jordan, do you have anything to add? An extra question or extra comment about his work? If nobody has something. Okay, apparently nobody has something extra to add. So well done, Joseph. Thank you again for your presentation. And I think we will stop this presentation here. Thank you very
Thank you
much.
very much. It was a good presentation, very enjoyable. Thank you.
Welcome.
Well done, Joseph, and thank you.